Thank you. Thanks for the organizers for inviting me here. This is a great summer school with already very well known. All the students want to come here, and also San Sebastian is a wonderful place, one of the best conference venues ever. So I will talk about quantum geometry and superconductivity. And there is lecture material, so of course I will put my lectures into Slack, so you don't need to write things down in that sense. But if you want to then go through the derivations in a more detailed way, I recommend this first. It's like a proceedings of a summer school, so it should be pedagogical, and there are details and so on. If you want more like a little bit more overall review, which goes to some depth but doesn't have so many equations, I recommend this recent review. It's also about how these things relate to TPG. I put some background material to Slack, so I assume that you know now BCS theory and some basics of quantum geometry. Maybe you knew them before coming here. Right, and then there is also an essay that I wrote recently. This is a very light and entertaining reading. You can read it like on a Friday evening with a beer or wine glass. So, and yeah, then if you are still interested on Monday, you can go back to this stuff. Good, so in the first lecture, I will tell just the basics of these topics, quantum geometry plus superconductivity. We start with quantum geometry. Part of it was in my lecture, this pre-material, but I just go through some easy stuff that you really understand, and then we go to the main point, like the basics. And the second lecture is a list of very many kind of the recent research topics and results that have emerged from these basics. So, quantum geometry, well, this relates to an object called quantum geometric tensor, which was, these people were inspired to write it down because they wanted to ask, is there a metric for distances between quantum states? So you take any quantum state, wave function marked with u, and this is some parameter. This could be the Bloch function and could be the lattice momentum, but now think it's general. And then it changed a bit this parameter, and you ask how does the norm change? And you can derive some kind of metric that it's a metric times the small change in the parameter. And if you make a gauge invariant version of that, you will get the object called quantum geometric tensor. And its imaginary part is probably something many of you have heard many, many times, namely it's Berkovits. And the real part of that tensor is this metric, that the small distance, infinite distance of quantum states when you change k is determined by this. And Berkovits gives you a Chern number when integrated all of Brillouin and so on. So topology of the system is also inside this quantity. But it's important to know that, for instance, this quantum metric, well, as you know, you can have some finite Berkovits and still zero Chern number. Also, you can have even zero Berkovits, but still finite quantum metric, and that has some effects. So this quantum geometry is like a, how to say, a weaker condition than topology. So your system might be interesting from the quantum geometric point of view, even if it's topologically trivial. But it goes the other way around, then if it's topologically non-trivial, it will also have non-trivial quantum geometry. Yeah, and this just, mathematicians invented this concept already more than 100 years ago, but they didn't know what to do with it, as usual. So then this is some lesson of life I want to give to you, that if you don't understand quite some physics concept and you're kind of afraid to admit that you don't understand it, then look at it in the simplest possible model system. Like, simplify it so much that it feels trivial. Then you have understood it. So let's look at this quantum metric in the in a Hilbert space spanned by two states, 0 and 1, so this could be a qubit or a spin system or whatever. That kind of quantum state can be completely parameterized by two angles, as you know. This is the Bloch sphere. And then your parameters that you should take derivatives with are this theta and phi, and you can easily calculate that the phi quantum metric is sine squared theta. Now, what does it mean? Well, let's go to the North Pole. That's where I come from. So there, this is 0, and your state is just 0. And of course, you can change phi here in the front, but that's just an overall phase of a quantum state. It doesn't mean anything. If you change phi a bit and take this overlap, you see, we are always just thinking about these overlaps or distances. The distance will be 0 because it's just an overall phase. So that's what this thing tells. And then if you are at the equator, sine theta is 1, so there is a finite distance. This reflects the fact that there you have a superposition of 1 and 0, and then, of course, if you change phi, you really change the state. You can even make it orthogonal to the original one if you change enough. So there, changing phi makes your new state to be a little bit orthogonal. So there is a finite quantum distance. So it's nothing more than this. How non-orthogonal or orthogonal the state is when you change some parameter. And this can vary where you are, depending on where you are in your Hilbert space, for instance, in a band, in a solid, where you are in the Brillouin zone. And here one more trivial level example. This is from my essay, so you see the level of the essay. So imagine now that you have a solid which has atoms, and atoms have some orbitals. So we have just two orbitals here. And then you can calculate your band structure, and you might get a band structure where the upper band completely corresponds to one orbital. And there, when you change a bit this k, you still have the same orbital state, and then the overlap will be really very good. So there is a 0 quantum metric. But you could also have these orbitals hybridizing, and in this way your bands, let's say here, they contain both alpha and beta, and now if you change k a little bit, you might change the alpha-beta content, and this makes the new state to be a little bit orthogonal to the original one, and your quantum metric is non-zero. So this is what it is. And people got interested in it only recently. These are the experiments which have directly measured quantum metric. They are mostly in optics. And also, this is from my group. We have also seen it, because that's my other life. We do some photonics experiments. But now, yeah. So that just to mention that it's new, but it has been experimentally observed. Now some math that will be useful in this lecture. So I gave this definition in terms of the wave function itself. You take derivatives, and then there is the wave function, and so on. But there is actually a very nice and elegant and somehow mathematically, even physically deep way of expressing these things. You can use the projector to the band of interest or the bands. So here I have a certain band, U of n, Un. It could be also a set of bands. So you define the projector. You know what projector is. You put it kind of measures how much my quantum state has content from that band. And it's Hermitian, and how to say, is there a name for this? It's square is the same as it is. I don't know, it's probably some name. Nicely also, you should remember, sometimes when you do calculations on this, that you have, let's say, some finite number of bands. Then the projector is the identity minus the projector to all other bands, obviously, because they sum up to one identity. And here in this lecture, because this will be Bloch functions. The projector is gauge invariant. You can put a k-dependent phase arbitrary factor in the front, and of course, because you have this form, it cancels. So that's nice. When you write things with the projector, you know immediately that they are gauge invariant. And of course, you already knew that this quantum geometric tensor is gauge invariant because I saw that there are experiments, so indeed it can be observed. But this is the form of the quantum geometric tensor expressed with the projectors. Now, the tensor is actually positive semi-definite, and this is the mathematical meaning of that wording. And then the real part of this, as I said earlier, is the quantum metric. So you can actually show that it will be just this thing, two derivatives of the projector and trace, and the imaginary part is the Berry curvature. So I will come back to this, why this is useful, but you can show it with these projectors quite easily. So as mentioned, you know that Berry curvature has been studied really hugely because it's there in all topological studies, and I don't even try to cite review articles here. Then with this quantum metric, it's another story. A few years ago, there were still very few papers that somehow connected it to physics. You see here a few examples, and we started this business in 2015. But then after 2019, I was unable to put all the papers on one slide, because people really got interested in this concept of quantum geometry, and large part of it is because there was twisted bilayer graphene superconductivity where you have flat band, and I will show soon that this quantum geometry is especially important in flat bands. But there are also other things, fractional chain insulators, some transport phenomena, and so on, even electron phonon coupling, they are influenced by quantum geometry. Good, so that was the basics of quantum geometry, and now let's go to superconductivity. What is the role of quantum geometry there? But let's start from the basics. So I assume now that everybody knows the BCS theory of superconductivity, and this is the critical temperature that it gives. Here, U is some kind of interaction scale, and this thing is density of states at the Fermi level. So unfortunately, this form is exponential, so it leads to very low TCs. And this is because in usual superconductors, the kinetic energy compete with the interaction energy, which is usually small because electrons, they naturally repel each other, but you need some kind of attractive interaction for superconductivity, and this could be electron phonon or some spin fluctuations, but those are leading to weak interactions typically. So these are the constituents, it seems. We could, if we want to go to room temperature, for instance, tweak the interactions or the density of states. And that's the flat band route, the latter one, that maybe we could remove the kinetic energy and maximize the density of states. So then interaction effects would dominate. And there have been ideas like this. So first so how do I define a flat band? So here you see the Bloch function of a usual band with some bandwidth. This thing, this U here, periodic part of the Bloch function, will be very, very important in this talk. We define the quantum geometry with this. Now this is a flat band. It could be like exactly flat, but it's also okay if just the bandwidth is smaller than interaction, you get flat band physics, and of course group velocity is 0, and it's an insulator. However, without interaction. However, when you put interactions and do a simple mean field theory, you can show that the critical temperature is now linearly proportional to the interaction and to the volume of the flat band. So this is of course good news, because for small u, this means exponentially enhanced critical temperature. Very good news. However, this is not the full story, because this Tc refers only to the, when do you get like absolute value of the bearing gap to be something non-zero. Because the order parameter of superconductivity is this type of object. And okay, the gap, the observable gap, is the absolute value. But this Tc only tells that you have a gap. But that's not enough. For superconductivity, many systems have a gap and they are not superconductors. So if you really want to show that you have a superconductor, you have to see Meissner effect. Or in more fancy way, you want to see levitation. But it's basically Meissner effect and supercurrent. And supercurrent is really fundamentally different from other usual currents. You see, it's proportional to the vector potential, while usual current is proportional to the electric field. This is conductivity. The thing here in front, which is kind of like the conductivity, is the superfluid weight or superfluid stiffness. It has two names for good reasons. I will tell you. Okay, so you must be able to have this supercurrent to have a superconductor. And you might got already worried that I have a gauge-dependent quantity there, the vector potential, but don't worry. Namely, the order parameter also has something that is not gauge invariant, so or let's say not observable. So the order parameter can have a phase, and this can have also spatial gradient and so on. And this is not gauge invariant either, but nicely, this combination is invariant under gauge transformation. And much of the basic phenomenology, actually all the basic phenomenology of superconductors you can derive by first assuming that you have an order parameter with some phase, and then demanding that you have some gauge invariant observables in electromagnetism. So this one is gauge invariant, and that kind of couples my supercurrent and the change of this phase with space. And from this you can show that actually the free energy change when you have some phase gradient here is given like this. There are derivatives of the phase times this superfluid density. So from this it has it looks like kinetic energy times something. So this is actually the inverse mass tensor of the Cooper pairs of the supercurrent. On the other hand, this thing relates to phase fluctuations. So therefore the two names, superfluid weight, because it's like the inverse Cooper pair mass, and superfluid stiffness, because it determines how much phase fluctuations affect your free energy. Then you can further derive the London equation, and you see that the superfluid weight is inversely proportional to the penetration depth. And this, of course, then gives you levitation in magnetic field, so this is really the crucial concept. So now we have to evaluate that one in a flat band to see whether we really have superconductors in a flat band. And then we seem to have a small problem. So this is the Landau-Lifshitz level results for superfluid weight. Here, electric charge, density of Cooper pairs, effective mass of a single electron, and then some temperature stuff you can forget about. But the essential thing is this inverse of the electron mass, which would be 0 in a flat band. So this seems now like, okay, fine, we can get exponentially enhanced pairing potential. There's a gap, but then nothing moves. However, this is a single band result, and this is not the end of the story. Namely, the flat bands that are of any interest, they are for instance, this kind of flat bands that are formed due to interference effect or frustration, if another wording for that. So trivial one would be the extreme atomic limit, where simply electrons are localized at atoms. But if you have certain geometry of your orbitals in the unit cell, for instance, like the Lieb lattice type, you might have states where you have minus amplitude here, plus here, and then when they try to tunnel here, they destructively interfere. So particles can be localized in these kind of compact localized states. So these flat bands are interesting, and you have them all over the place. I think in this summer school you have heard about the Kagome materials and many others. So this is, for instance, the Lieb lattice, and then there are Moir materials, twisted bilayer graphene, and so on. And there, the story is more like that. Okay, you induce a superlattice and you flatten your bands. These are actually the same thing, but one more in the real space and the other one in the momentum space, and of course Landau levels and so on. So with this kind of flat bands, now if you really want to understand things, you have to do multiband theory. And this is what we started to do 2015. So now I tell you the basic results of all this, I mean our early work, and not paper by paper, but more like, yeah, in the mind. So I introduce all the co-workers at once. So there are a few really important people from my group, Sebastiano Peotta, with whom we started this business, and then Long Liang was a very important early postdoc, and Kukka in our recent work was really a key person. And then, yeah, some others from my group and local people. But then I also had very important collaborations with two outside groups, so Sebastian Huber and his student, and lately with Andre Bernevik and Jonah and Aaron from his group. So let's go to what we did, and here we start with a mean field theory. I will show beyond things later, but let's just do mean field theory, but now in the multiband context. And we take a Hubbard interaction, so here you have attractive interaction between the electrons assumed somehow. We don't specify how do we get it. Hoppings and chemical potential, but the important thing is this alpha and beta index. So they are the orbitals. I and J are lattice sites, and these are orbitals, and they have to be explicitly there. Then we calculate this key quantity superfluid weight. And we do it by introducing a supercurrent. You can think that, okay, my order parameter has this kind of, this is Cooper pair momentum times R. So Cooper pairs flow. And then I calculate how much does my free energy change with this current. So that should give you the superfluid weight. Then, as I said, this is the gauge invariant quantity, so somehow these two approaches, the phase of the order parameter and having a vector potential are connected, so you can equivalently calculate superfluid weight also as a linear response to a vector potential. And this gives you exactly the same result. There's a good sanity check always to do it both ways. And here is the result. You can read the details from the lecture notes that I gave, but I cited. But let's go to the main result directly. So we found that the superfluid weight has a contribution that everybody knows, and we called it conventional, and that's proportional to the derivatives of the dispersion. So the inverse of the effective mass of the electron, and that would be 0 in a flat band. But then we found that there is another contribution. And this requires a multiband system, and it can be non-zero also in a flat band. So that's the good news. There can be current also in a flat band, supercurrent. And we call it geometric because in certain limits we can show that it's linearly proportional to the interaction, and this quantum metric, the quantity that I introduced, which seemed to be very abstract, just some distances between quantum states, here it appears in superconductivity. That's cool. So let's try to understand it. But here I want to show some, look, these are actually, we have very general but very complicated formula for this. So I want to show how it looks like in some simple cases, because I try to advertise to you this approach that simplify things until it feels trivial to you. So you can get much simpler results if you assume time reversal symmetry. Again, our results are more general than that, but if you assume this, you get nice formulas. So the hopping matrix has this relation, and then with time reversal symmetry, you can drop the spin index because your single particle energies, these are the same, and we just use this notation. Then we do a further, this was an assumption, and then we do further assumptions. Let's not now assume that a flat band is isolated, meaning that it has a band gap to the other bands, which is smaller than your interaction scale. And of course, interaction has to be bigger than the bandwidth to be in the flat band limit. Then we further assume that we have a so-called uniform pairing, that if we have pairing in some of the orbitals, it's the same in all orbitals. And this is actually the case if your orbitals are related by symmetry. So with these three assumptions, the superfluid weight formula is very simple and proportional to the quantum metric. So it has interaction, filling, new number of orbitals, this dimension, and here this one is the minimal version of the quantum metric integrated over Brillouin zone. So remember the imaginary part of the quantum geometric tension, namely the Berry curvature. If you integrate that over Brillouin zone, you get Zer number. Here you take the real part, integrate, and you get something that completely determines your superfluid weight in a flat band. It appears in other contexts also, but it seems to have some deep physical meaning. And yeah, so these formulas you can get by mean field, but also by an exact treatment in some limiting cases. And furthermore, in this flat band limit, you can calculate what is your delta. It's given directly, it's again linearly proportional to interaction and filling like this. And if you use this, there is an alternative formula for superfluid weight. It's proportional to the delta squared times this quantum geometry stuff. We will come back to this when we talk about experiments later. Now I show you a bit more complicated formulas. If you have more general case, you still have relatively nice analytic formulas. Here you see the conventional one is proportional to the derivatives of the dispersion, will be 0 in a flat band. And this is how the flat band, the geometric one looks like. Quantum metric is not explicit here, but this tells something about the physics though. Oops. Yeah, okay, yeah, it's on this slide. So, so this is the geometric part, and it contains this kind of things. And why do they come up? Well, if you calculate this thing, for instance, by this route, like linear response, what you will have here is a current correlator. And the current operator, if you have some hopping matrix, it's defined like this. It will have two parts. There is one that is proportional to the dispersion, coming like directly from the derivative of this one. But you need to take derivatives of the Bloch function also. So there is another part. And now, if you have these things in the current correlator here, it's kind of plausible that you get something that has derivatives of the Bloch functions in the superfluid weight. So this is, if you want, if this it helps you, you can think that okay, in my current operator, I have the dispersion contribution, but I also have this, which is given by interband processes. So here N and M are different bands, and you see it's of course 0 in a single band. So that's why this whole quantum geometry stuff is really multiband stuff. You need to have multiple bands, and then you get these. You can think about this as also like virtual processes where you have current via going to the upper band and coming back. So that's what. Then it's maybe easy to understand. You could get some current. Yeah.
Does this mean that within the flat band you need to have multiple quantum numbers, or do you need to have multiple bands, flat bands, separated by a gap?
No, certainly not multiple flat bands, but you have to have many bands in your system.
Okay, but within the same flat band you don't have to have multiple quantum numbers?
No. You can kind of consider the flat band as such and do all your interaction physics there. But then you have to take into, when you calculate, for instance, this, you have to take all the bands into account. Yeah. Okay, this was very good. I actually wanted you to ask questions during the talk, so others, please also get active and interrupt me when you feel like that you don't understand something. Good. So I mentioned that this quantum geometric tensor is positive semi-definite, and that allows one to derive this kind of bounds of superconductivity. So, for instance, one can show that the superfluid weight is always positive if there is at least somewhere in the Brillouin zone finite pericurvature. And also, certainly, if your band is topological, then you will have this type of quantum geometric supercurrent. So topological flat bands are good, but it doesn't need to be topological. This can be 0. You can just have a finite pericurvature. Or there are even systems which have 0 perikurvature but finite quantum metric. And it still gives a supercurrent. So if you remember, I said beginning that in our approaches of increasing TC, we could look at the interactions, try to make them bigger or make the density of states bigger. But now we know there is a third thing that we should think about, the structure of the Bloch functions, because this quantum geometry and topology, it directly affects superfluid weight, which tells whether you have current, and actually superfluid weight in 2D, it also gives you the PKT temperature. So that's something that you now can utilize and should not forget. Good. So, yeah, maybe I already, yes?
When does the inequality become complete?
I think if I remember correct, I don't do that research myself, but for Landau levels, you can show that it's quite tight. Is it so? Anybody in the audience is an expert? So there are some systems where it kind of becomes strict, and if I remember, it's Landau levels. Yeah, so I already gave some intuitive understanding, but I would like to give a bit more. And actually, yeah, 2017 or 18, I had in mind that I want to understand much better this thing. So I thought that it would be nice to try to reproduce what Cooper did. You know, the famous Cooper problem, he just took this is also my passion of simplifying things, just two particles and the two-body problem. But not only the two-body problem, but also assuming that the scattering is restricted by the Fermi sea. Maybe you remember from your courses this thing. At least two-body problem you have solved in some elementary quantum mechanics course, and then Leon Cooper just restricted the final scattering states because there is a Fermi level. And what he got out is this, the same result as from BCS theory. So it was quite inspiring at that time that you could get the TC for pairing from the two-body problem, and just the essence was the existence of Fermi C. So let's do something similar. Solve the two-body problem, two particles interacting with some potential. But of course, we have a problem even in the start, because this was, Cooper's work was based on having a Fermi C. And now the flat band is exactly the thing where you don't have Fermi C. However, the thinking now can be and must be very different. We don't have a Fermi C. Instead, we have a large degeneracy of possible states in the flat band. All case states have the same energy, so particles don't know really where to go. And now in the two-body problem, we can ask that, okay, if we put two particles there, if we make them interact, what happens? Can the pair actually move, even if the single particles can move? So is there an instability towards making a dispersion to the pair, even when the single particles are localized and the dispersion is flat? So let's see what happens. And of course, this is what happens. So first of all, you have always a bound state. And our friend, the Bloch function appears here. So Q is now the center of mass of the pair. This was the potential, and X is something like the orbital coordinate, strength of the interaction. And if we assume again this uniform pairing, we get quantum metric out. So from here you can develop this with Q squared and so on, and from there you get the inverse effective mass of the pair, and it's given by the integral of the quantum metric. So, and since the superfluid weight is basically inverse of the Cooper pair mass, we get the same as the multiband mean field theory result. So in nice analogy with the Cooper problem and BCS theory, also here two-body problem in a flat band gives the same result as the multiband BCS. And that also gives you maybe some intuition now that, okay, when a bound state is formed in a flat band, it actually gets dispersion. And here is a comparison now between the Cooper problem in dispersion and flat bands. So you start with here finite mass, here infinite mass particles. The pairing energy looks very different. Here it's exponential, like this is the gap or TC, and here it's proportional to the interaction. Also the Cooper pair effective mass, completely different. Here 2 times single particle, here interaction times quantum metric. So the Cooper pair mass is completely quantum geometric here. And yeah, here Fermi C is needed, here, I mean here is needed, here not. And in both cases there is no interaction threshold. So then another way of looking at this problem, it's actually a bit related to this, is that now think about 2 types of flat bands. This kind of trivial one, where you have just atomic limit, electrons bound very tightly around the atoms. And then this interference caused flat band, where you might have your one-year functions a little bit spread out. Now if you add interactions here, you just get something like on-site pairs or something. But in this case, when you add interactions, somehow you cannot disturb maybe the interferences, and you get movement, and the movement is possible whenever there is a one-year function overlap. And that connects to all these geometric things, because actually this quantum geometry and so on, it has been used for describing the localization of one-year functions. And it has been, for instance, showed also that if you have a non-zero Chern number, then your one-year functions cannot be exponentially localized. So that makes quite understandable this inequality that we derived. Yep.
So this is about the previous slide, actually. So normally when you have a regular dispersive band and you crank up your strength of interaction,
Yeah.
then you have other instabilities.
Yes.
Charge density
Yeah.
etc. Is there some reason that in a flat band you're protected against other instabilities?
No, you are not protected. You always have to compare. So this is just what happens if you assume superconductivity. Of course, in the two-body problem, if we plug in attractive interaction, we really know that we get one Cooper pair and so on. But in the many-body system, you have to look at the different instabilities. So this, for instance, this is a bound only in the sense that if superconductivity, that it is possible that there is superconductivity, but it's also possible that some other order wins. But people have studied some flat band systems, and at least in some systems, you really do get superconductivity, like even in a more advanced methods like quantum Monte Carlo and so on. Yeah. So, because the one-year function localization is related to quantum geometry, this also is quite understandable. And then if you think about what the current is in the usual parabolic or other dispersive bands, the physical picture is like that you have a global shift of the Fermi sphere, and basically it's just the particle density and effective mass of the single particle that matter. But in a flat band, it's all due to delocalization of one-year functions and then that interaction-induced transport. And here I see a nice analogy to something very old by Anthony Leggett, that he studied supersolid, and he was showing that in order to have a supersolid instead of such a density wave or something, you also have to have a connected density. So basically these overlaps of the one-year functions. Right, so these results that I shown were just mean field and two-body problem and so on to get the big picture. But there have been a lot of further study. So for instance, we have shown that in some contexts actually BCS state is exact in flat band. That's a big surprise, or maybe not so big. Anyway, then there are various advanced numerical methods and also exact results. So next I will say some exact results. And those exact results are based on the fact that if you take a system, a multiband system, which has one flat band, and then you project your Hamiltonian to the flat band using these projectors that I introduced, you can actually show that the Hamiltonian can be written like this. So it has only interaction energy because you have projected to the flat band. So flat band always has zero kinetic energy. But it has this interaction energy, and here is the density operators in the flat band, and it's quadratic here. And this is a positive semi-definite Hamiltonian. That helps a lot, because if you find zero eigenvalue, you know that it's the ground state. Very nice. So based on that, which was derived in this early work, we then did, together with Andrei Bernevik's group, this exact treatment. So here you see how the projection works. So you define operators of the flat band using this projector that we looked at. Here we can have many bands, many flat bands, for instance. And we assumed, again, this uniform pairing condition which you can now write like this. So this is the number of flat bands, number of orbitals, number of unit cells. And this simply means that if you have in the orbitals where you have pairing, it's the same size of pairing. And then we use this Hamiltonian, positive definite Hamiltonian, and found that there is a ground state of eta pairs, so-called eta pairs. So you see, this is like a sum of all Cooper pairs in all momenta, and then you have just n of them. This is an exact ground state of this Hamiltonian. And very nicely in this ground state and with this Hamiltonian, the Cooper pair excitations are governed by an effective single particle Hamiltonian, which is composed of these projectors. So this gives you the excitation spectrum, and it's a single particle Hamiltonian, so you can kind of trivially solve it. And from that, you get, for instance, the mode that would correspond to supercurrent, and there you see the inverse effective mass of Cooper pairs is proportional to this minimal quantum metric that I showed before. So you get this result basically from multiband BCS mean field theory, from the two-body problem, and from an exact treatment. So that's quite nice. And all other excitations as well can be found from this. And by the way, this uniform pairing, in the early days when we introduced it already 2015 or something, we thought that, okay, that is just something that gives us nice results. But fortunately, it's not some kind of special case. It's actually can be quite general in many materials because it's completely valid when the orbitals of your system are related with the symmetry, are related by a symmetry of the whole system. So of course this is not true in all materials, but there are even real materials where it's fulfilled. Now, I have given the results for isolated flat bands, and that's made this isolated flat band limit mainly in order to get nice analytical results, which you can understand. But actually, in our quest of increasing TC, that's not the best possible option in general. Because numerically, we can, of course, calculate all kind of cases. And for instance, if we take the Lie lattice, where you have a band touching here, then we can do some tricks to open also a band gap and compare the situation. And here we calculate the BKT temperature. So in 2 dimensions, the critical temperature of superconductivity is given by the quantum metric, by the superfluid weight in this way. So we calculate that when we have no gap here or some sizable gaps. And you see, the no gap situation is the best. Here with the bigger gap, we get this linear dependence on interaction. Here it's even better. It's like a sublinear, so to speak. So it's nice to have band touching. It's just that we don't have so tangible, nice theory for it. And that's one of the exciting future goals in this business, to have some kind of analytic, nice theory for the band touching case, and then we can design room temperature superconductors. Here, this figure shows also another key point. You see this line? This is usual square lattice. So for very large interactions, it's way better. So it's not that the flat bands are the best always, but here they typically really win in the small interaction. This is in the scale of the hopping in the system. So when you have about the hopping scale or smaller interactions, then it's really exponentially enhanced, the TC. So in kind of relatively weak interaction systems, it's better. Yeah?
So you have to come absolute magnitude of TC. You want to increase, go towards room temperature.
Yeah.
That's a different story from saying TC is high if you had a particular, compared to, there's some Fermi energy, EF over bandwidth, some energy scale or interaction over bandwidth energy scale. So TC is high compared to that, but it doesn't mean that TC is going to go all the way to room temperature.
Yeah.
What I'm saying is that TC is relatively high for a flat band, but it doesn't mean you can crank it all the way.
Yeah. This thing here that, okay, it's linearly dependent, but of course, if you crank the interaction up in your system, actually soon you will employ all the bands there and you get localized particles and so on. But I mean, it may help you if you, let's say that you have a system where the interactions are relatively weak, then you might, if you can go to the flat band regime, you can actually increase TC. Yep.
Would it make any difference how many bands are touching? So for example, if the flat band comes from a surface permeate that then has no dispersion, then it touches with the bar, is it better, worse, the same?
I would say that in general it's better, but of course it always depends on the system. But you see, the quantum metric is usually concentrated around the area where the other bands are nearby. And the band touching case, of course, then the quantum metric diverges, so you cannot use that as a measure anymore. But these quantum geometric effects are kind of maximized. So I would say that if you have many touchings, it will be in general better. Okay, and here is another, just in another model, the same story that this flat band thing, the BKT, it's much better in the small interaction regime. All right, so now I want to come to something. So in my essay, I coined this kind of sentence of wisdom of life that the devil is in the supplementary. If you really want to do progress in physics, you should read carefully the supplementary materials of other people's papers and also the papers of your own group, the papers, supplementaries of the papers from your supervisor, and this is what one of my students started to do when we get some crazy results. So I say, this was our original work, and this thing was the result, and now maybe it looks, yeah, I have seen this result, but there is something missing here, and there is a problem. This superfluid weight, it's independent of orbital position. So for instance, if you have a Lie lattice or some material and so on, you could think about moving these positions in real space. And this, your intuition maybe should not matter, and indeed for superfluid weight it doesn't matter. But all these quantum geometric quantities, Berry curvature and quantum metric, they depend on the orbital positions. And so we have here an equation where this side doesn't depend on orbital position and this side does. Actually, we knew it for quite a while, but we just shrugged our shoulders like, yeah, maybe one day we solve it. Okay, one day we then solved it, but I can show, because we may, yeah, we even knew this thing, but we thought, oh, this is some one-day stuff. Because there is a way to show how wrong this can be. Take the SSH model, and you can calculate the quantum metric. These are the two hoppings. And for this condition, if you put one of them to 0, that you have really disconnected dimers and no current can flow, okay, you get zero quantum metric, nice. But for this other condition, if you put one of the hoppings here to 0, you still get a finite quantum metric, as if some current would flow, and this is completely wrong, of course. Now, fortunately, this can be solved. So actually, all this story is still valid, you just have to use so-called minimal quantum metric. So you would think that you could vary the orbital positions and you take the minimal value and that will be related to the physics. Like here, you would always take the 0 in the disconnected case. And yeah, so these are basically the key papers on this. And how this comes about? Well, for the superfluid weight, we have to take this derivative of the free energy. And if you really do it carefully, it's a partial derivative. And then something like this. And by the way, the student who did this, Kukka Huhtinen, she told me that one thing that really helped her in this was that she was a TA for students, and she realized that students had huge difficulties understanding the difference between the full derivative and the partial derivative. And there is really a difference between. Okay, so here it's partial derivative plus some stuff. And this stuff is related to the imaginary part of your order parameter. So it's something like this. It's very easy to say that, okay, I choose a cage where all my order parameters are real, which you can always do in a single band system. But in a multi-band system, this is tricky. It can go wrong because then you have to also think about the order parameter when you plug in Q, and you just cannot make a gauge transformation that makes all orbital order parameters real. So in principle, you should keep this. And and if you make any transformations to kind of remove this thing, so then you would also change this. And in all the literature by us and many others, only the partial derivative was considered, and this part was kind of just one sentence in the supplementary that this can be caged away, that it cannot. So, however, you can still show by this formalism that if you use the minimal quantum metric, then it's okay. So it effectively takes into account this part. And now you might think that, oh, but that's terrible that I have to minimize the quantum metric with my orbital positions. Fortunately not. We have also shown that if you place the orbitals in the high symmetry positions of your system, then the quantum metric is automatically minimal. And by the way, for this reason, many of our numerical calculations happen to be completely correct because the orbitals were very symmetric. So for instance, in Lie lattice, the symmetric one is when this blue and yellow, red and yellow orbitals are in the middle. But you can change their positions. And here, so this is the symmetric one. And this is without any gap between this tunes the gap, and then you can choose the positions by varying this parameter A. So when there is no gap between the Dirac cone and the flat band, you see that the real superfluid weight should go like this, but some orbital positions give you wrong result. And also here. And this is the most dramatic case, because when delta here is 1, so you basically have isolated sites, should be no superconductivity, still some of the wrong orbital positions claim that you would have superconductivity, while the correct one and the full formula give the right result. So, but if you put the orbitals to the high symmetry positions, then you get the right result. And I'm not exactly, how much do I have? Yeah, no, I'm almost in the end, yeah. Okay, so this is the, kind of a summary that or a reminder that we have also a more general case in the papers, not only these simple formulas I have shown. And if you want to study about this topic, this is the first paper. This is easy to access review. I hope it's easy to access. And then these formulas with the corrections, this orbital position stuff, they are in this one. So if you really want to use the formulas, look at these two works. And by the way, this basis independence, it's also, in other words, that you have to do RPA, because it's basically that if you apply a vector potential, also your order parameters change in some kind of self-consistent manner. So then I want to advertise you, if you are looking for postdoc now, or in the postdoc position now, or in future years, we have a newly funded Simons collaboration, at least these years, maybe until that one as well. And in September, there will be positions open. And these are the people. Here, Andrei Bernevik is the boss, and me and Andrei Subukov are also like co-leaders of this activity, and there are others that you know, for instance, Eres, who is in the audience. And some of this group will have now soon open position, and if you are interested in my group, I'm here, you can discuss. So this was the end of the lecture 1. Thank you.
Hello, thanks for the nice talk. I have maybe a very naive question. Like, in the table that you had where you were comparing Cooper's result with the flat band things, so for example, for the Cooper pair effective mass, like, it's super easy to understand for the dispersive model. It's a Cooper pair, there's 2 electrons that are bound. But like for the flat band case, is there a simple way to understand how this quantum metric is manifest? Like U0 times quantum metric equals to effective mass. That's difficult to understand. Like, where is that coming from?
Yeah, it's just that all movement in a flat band, in this case, is some kind of interaction induced. So the interactions induce your hopping. So that's why there is U. And then this quantum metric guarantees that you have overlaps of the initial one-year functions, because if your electrons would be really localized on atomic sites, then you couldn't have movement. So but it's a little bit, you have to think about it.
And what is it that's carrying the current, the supercurrent?
They are still these pairs, but they just move kind of induced by interactions. But of course, in an abstract level, you have an order parameter, and the phase changes spatially. That's your supercurrent.
Okay, thank you.
Thank you for your talk. I was just wondering about these symmetric positions to obtain the right results. Mm-hmm. So what do you mean by the most symmetric? Is it like the most symmetric Wyckoff position for this lattice and the set of the symmetries? And
yes, I don't know whether I have but it's basically if the orbitals are in such positions that they are related to the other positions by a symmetry operation of the system. So yeah, for instance, here, if the Lieb lattice, if they are in the middle, you can rotate the system and you get the same. But if you put them elsewhere,
maybe could you also give an intuition why it should be like the most symmetric one? And
for that I do not have an intuition. Yeah, it just found it. Maybe there is something. Maybe you can think about it. Yeah.
Okay, thank you.
So I just wanted to make sure I understand the issue about the dependence of the position. So can I think about it like this? If I have some orbitals and some positions in the unit cell, and I want to pass a current, so I create some phase gradient, but now the phase gradient doesn't have to be uniform within the unit cell. So I have to kind of optimize over the relative phases of the order parameter on different orbitals, and that's where this dependence on the position comes from. And you say if the orbitals are at some high symmetry positions, then it has to be, then the relative phases are dictated by symmetry or something.
Actually for the superfluid weight, if you just bluntly calculate it, the orbital positions don't matter. So for supercurrent, physically, they don't matter. I think it's just because it's like a property defined at the unit cell level. However, if I want to connect a superconductivity in flat band to the quantum geometry, there I have to, when I calculate these quantum geometry quantities, I have to choose certain positions. So that's how it's working. And how to understand why do I have to choose the symmetric ones, I really don't know at the moment.
Actually, I have a similar confusion, but I'm maybe going to phrase it differently. If you have disorder and you don't know what's the unit cell, or you don't really know what are the high I can still formulate a real space version of the metric just by Fourier transforming. And so how do I find the minimum?
Yeah, I mean you cannot use this theory then at all. But people are working on it, that there are results on disordered systems. So disordered flat bands, you still have some superconductivity, some supercurrent, and some people try to indeed use the real space version of quantum metric to study it. But you cannot use these results that I showed.
Thanks.
Do you have any intuition why you have this? When you define this minimal metric, okay, so you have either 0 or 1/2, so it looks like you have something that is defined not modulo 1/2, but similar to polarization and so on. When there is an interpretation of what you get modulo electron charge, do you have any intuition why you get this exactly 1/2, and if this value is general for other systems also? Is also this always modulo?
I don't know. I mean, these exact values here, they are specific to SSH model. What makes sense is this one, for instance, that if I really disconnect the dimers, I should not have any current.
You should have zero,
But why this is half and where does it come? I don't know. But it's just showing that this quantum metric can give some results that do not have any physical meaning in the superconductivity or conductivity context.
Okay, thanks.